The speaker is Prof. Paolo Casari, which is Associate Professor at the University of Trento in Italy. He received a PhD in Information Engineering in 2008 from the University of Padova. He first was at the Massachusetts Institute of Technology in 2007. He worked on many European and US funded projects, and he's currently the PI of the NATO SPS project SHIELD. During his career, he first joined the Indea Networks Institute in Spain in 2015, and then from 2019, he joined the University of Trento as associate professor, where he co-leads the MANTA lab. Professor Casari is also in the editorial board of the IEEE Transactional Wireless Communications. He received 2 Best Paper Awards, and among his research interests, we can find many aspects of communication system, let me say, channel modeling, network protocol design, localization, resource allocation, simulation, and also experimental evaluation. So now I leave the floor to Professor Casari for his tutorial. So remember that any question will be given at the end of the tutorial. So please, Paolo.
Thanks a lot, Dario, for the very nice introduction. Thanks everyone for taking your time to be here tonight at this tutorial on telecommunications organized by Restart. And I start by sharing my screen. And the title today is A Tale of Friends and Foes. It will become clearer later. We are talking of friends and foes, but what we will be talking about today is underwater communications, especially underwater acoustic communications, and how something that is normally regarded as harsh, so communication channels in particular, can be actually used for localization and security and can help these tasks. So first of all, let me acknowledge my many great collaborators from many different phases of my career. I like to present this picture. I try to keep including more people in this one because it looks nice. Pictures are from 20 years ago, at least in my case. So you also see time passing. And besides giving a thanks to all of them, let's start from a bit of an historical perspective. This is a tutorial, so we wanted to also set the stage for what happens in terms of underwater communications over the years. We start with a bit of national pride. So it was Leonardo who first devised that you can just put a tube underwater and you can orient it towards the source of sound, and it gets much easier to listen to that sound and understand the direction of arrival. So basically, he invented the sonar in a way, or at least a first example of the passive sonar. And then if you look at the next years, there is not a lot of important things for the field of underwater communications that got investigated in the physical domain. So, for example, we have some first measurements of the speed of sound, were quite often. We have investigations on magnetostriation and piezoelectricity, which are basically the phenomenons we leverage to produce sound and to actually detect and sense sound fields. And then somebody implemented a rudimental smart receiver with 2 tubes where you could infer the direction of arrival of sounds in a much more precise. Until we came to, well, the late 18th and 19th century and the 20th century. So basically, they started to understand how to do distance measurements properly using underwater bells that are very good sources of sound. Until we get one of those cases where your invention is just a bit out of time and someone, Lewis Fried Richardson, invented an underwater sound system for echo ranging, except he didn't think it should be patented, and except in 1912, the Titanic sank. And Fessenden, 2 years later, patented the system, a refined version of the system, as a system for iceberg detection. So this is one of those cases where you rebrand things and they have more success. Underwater propagation was started to be regarded as an interesting phenomenon, and during the world wars in that period, there were the first studies on how these sounds propagate, because it was, of course, relevant for military applications at the time. So, for example, the idea that there exist such things as convergence zones, where in deep waters you could have an upward refracting propagation and the sound would be propagated downwards, but then come back up, and converge and be detected reliably at different locations depending on the hour of day would also be considered at that time. So Paul Langevin and Robert Boyle were credited with the first proper sonar, and that invention came and made at least Paul Langevin national hero in France. If you visited the Pantheon in Paris and looked at the tomb of Marie Sklodowska-Curie, just beside that tomb, you see the tomb of Paul Langevin here, and he has been, of course, buried among the heroes of the nation for this milestone invention. So in all of this, where do communications come in? Well, communications always come in with applications. So you can, of course, devise the same applications that work for sensor networks, but in a much larger domain because oceans are the protagonist of the territory on Earth. So environment and infrastructure monitoring, environmental monitoring in general, including the localization and tracking of objects, as well as marine fauna. You could devise application in support to navigation and distress calls. You could devise port area control and littoral water security and security of underwater infrastructure. In general, one of the reasons why we investigate underwater wireless, specifically communications, is because it may make it much more economically viable to install infrastructure and to monitor it and to possibly act on it. And in particular, if you think about these very costly underwater cables, if you could reduce them, it's easier to make them waterproof. So if you could, for example, carry data, not by cables, but by wireless connections, that would make the whole infrastructure much less expensive. So the technologies that are typically used to communicate underwater are acoustic, radio, and optical. Radio and optical are much like free space radio and free space optical communications in terrestrial contexts, except that water is partly conductive, so radio communications fade after short ranges. In short ranges, they could be good. Optical communications are even better in terms of bitrate, but again, the range is short and they are subject to alignment if you are using lasers, alignment issues. Underwater, everything moves, so it's difficult to keep alignment. Acoustic communications tend to be the technology of choice if you want to deploy over distances of interest, a few hundred meters, a few kilometers, maybe. The only thing is the channel is very, very harsh. It is regarded as very harsh. Normally, for communications, you have very strong fading phenomena. You have very long channel responses, so you hear a lot of echoes, and these echoes last a lot of time with respect to the typical operations of wireless receivers. So we're talking about, in technical terms, we say that we may hear echoes for tens or hundreds of milliseconds. So we have hundreds of milliseconds of delay spread. But still, for many applications, acoustic communications are what is the most useful technology. So we will concentrate on acoustic communications in this part. Acoustic communications have quite peculiar attenuation law underwater. So if we compute how the signal attenuates as a function of range and frequency, we are looking at this term over here, which corresponds to attenuation in air. And we have this second term, which corresponds to a further attenuation that is frequency dependent. And if you plot this is called an absorption factor. If you plot it as a function of frequency in kilohertz, you see that it increases quadratically with this term in this formula that represents the function dependency of this term A of f. So basically, the more you move up in frequency, the more attenuation you may have, and therefore the more your range is limited. So most of the practical systems actually work in this area over here. Noise is also frequency dependent. So if you look at the noise, you see that there are several components, but regardless of these components, if you plot the power spectral density of the noise as a function of the frequency, you see that the power spectral density decreases initially and then increases again. And then the specific shape may depend on some parameters of the power spectral density function. So how much shipping is there, how much wind and wave breaking is there. So in general, the trend is the same. The trend is decreasing and then increasing. So you have, this is the typical thing that you introduce when you talk of underwater sound propagation. In terms of link loss models, one thing, the attenuation increases with frequency. One thing, the power spectral density of the noise decreases with frequency, except a later increase over here. So there must be an optimum in the middle. And the optimum in the middle can be found by computing the SNR and looking at where the frequency-dependent components A and W start giving you the best conditions. So the best conditions can be found in a graph like this. And first of all, because the frequency-dependent components also are here in this term, which depends on, then if you look at this plot, basically tells you the frequency-dependent component of your SNR. So it's basically proportional to the signal-to-noise ratio that you would have in your system as a function of frequency. And for different ranges, each range is represented by a gray curve. You see that the practical bandwidth that you have, typically defined as a function of the using the minus dB empirical rule. So the interval where your SNR decreases by 1/2 with respect to the best point. Well, those values tend to stretch and to increase in frequency when the distance decreases. So for short ranges, you can expect a few kilohertz, tens of kilohertz of bandwidth. For typical ranges, 1 to 5 kilometers, you can expect maybe a few kilohertz, maybe 10 to 20 kilohertz of bandwidth, but you see that the frequencies are lower. And for either ever increasing distance up to 100 kilometers, you see that you shift much lower in frequency, and in general, your bandwidth tends to become much smaller. So these effects are taken into account in the design of the transducers and are important because they limit the capabilities of the communication system. So another peculiar point is that sound in water is different than radio in air, and it propagates much slower. So we're talking about 1,500 meters per second. 1,500 meters per second gives rise to significant propagation delays with respect to typical packet transmission times, and has an impact in the design of the communications per se. So it is a bit more complicated than that, because it's not granted that sound speed is constant. Actually, sound speed is not constant, not with location and not with depth. So let's take one of the islands of the Italian Tuscany archipelago, and you get a sound speed measurement in August. This is the sound speed over the x-axis as a function of depth over the y-axis. So you see that for increasing depth, it increases. This is because it decreases, sorry. This is because, for example, surface waters are warm. We're talking about August here, and deeper waters are cooler. So basically the sound tends to decrease, and there is not enough pressure to make it increase again. In this case, we're talking about winter, so we're in February, and sound speed is almost constant, a few meters per second of difference as a function of that. So if now you run a ray tracer, you use a software that takes the environmental conditions into account and outputs how the sounds propagates, the various intensity patterns that you can get over a vertical slice of the water, you get outputs like this. So in August, for example, because the sound speed is higher at the surface, refraction gets most of the power to concentrate towards the bottom. The bottom is this line over here. Some of it propagates into the bottom, as expected. But in winter, it's quite different. In winter, you would get much of the sound to propagate uniformly, but because the profile, if you looked at this slide, the profile was upward refractive. So you see that there is more sound speed at the bottom than at the surface. So sound speeds tend to go up, and this can be seen by the energy concentrating over here. So all of these effects are to be taken into account when you design a proper network, because simply it is quite different what you get from what you would obtain from a simple path loss model, of course. So in general, this is a comparison. You see that a path loss model would predict a much more uniform path loss. So it has to be taken into account. So in order to provide, this is one of the first contributions that came from the start, by the way, in order to provide a way for everyone to actually implement the same kind of analysis in MATLAB and Python also coming soon, we provided this Hydromate software, which has been made recently public at this website, and that helps basically interface develop. The thing is the ray tracer requires a lot of environmental data, so this tells you how to download it. It's not our property, so we do not redistribute it, but you can download it freely from the web, and how to install it and how to run in such a way that you can tell the ray tracer, look, I have a transmitter at this geographical location with the coordinates and the receiver here, and it gets you automatically all the shape of the bottom, the depths, and so on, and it tells you how the sound would propagate. So, for example, for these two locations near Australia, you would get this kind of propagation with a few convergence points and so on. So, having said that, this is similar for those of you that maybe used or knew that there exists such a software named Desert Underwater that was developed in the years between 2010 and following. There was a similar library that connects to that Desert Underwater done much earlier. It's called the World Ocean Simulation System. Because these two are deeply connected, we wanted to also provide another, let's say, user-friendlier interface, and that's Hydromate. So we've talked a bit about why underwater communications suffer harsh conditions. We now talk a bit about another type of harshness, the one related to doing experiments. Experiments are important because nobody believes you in this community if you do not prove that something actually works at sea. So, well, let's start from an experiment that is kind of dated. It was done 15, 16 years ago. But it has all the necessary ingredients. So this was organized by the NATO Center for Maritime Research and Experimentation, different name at the time. But it had the main objective to try this waveform that was to be standardized in the forthcoming years, called Janus. And in the meantime, you exploit the waveform to do other tasks and see if you can leverage more information out of it. And well, if you are savvy about Janus, you would recognize this is the first version of the standards. So it has some preambles for waking up a receiver and for doing some general estimation. This is a hyperbolic chirp. And then it has some frequency shift keying encoded bits with frequency hopping. So depending on the frequency where this energy appears in the spectrogram, energy is the whitest, of course, then you would decode the bits that correspond to the message. Now, the experiment took place in Pianosa. That's why also the island of Pianosa earlier on. And the experiment was basically done over there with these objectives. The pros of Pianosa are that the location was almost flat bottom for several kilometers. The cons are that there's sometimes a lot of bad wind, which hinders experimentation, especially if you do it with a research vessel with some peculiarities. So the research vessel Leonardo here was one of the availabilities of the NATO Center, and it has several pros indeed. For example, large load area, sizable indoor lab, cranes to deployments, and automatic differential GPS-aided trolling motors. So you could stay in position very well. And a flat bottom. So if the sea is calm, you are very good at station keeping. So that's all very good. But the flat bottom is also your enemy. If the sea state is 3, if the sea state would be more than 3, the ship wouldn't even leave port. So in general, pros and cons. And yeah, a few pictures. So the deck equipment, you could see it over here. And for example, it has a lot of space for, you know, rubber boats and other kinds of equipment. And also wear long pants when you walk around. Otherwise, it would be my knee and not my pants to be broken here. but practical things you learn when you do this kind of experiments. And then the indoor lab of a ship like this would basically be with a lot of friction, high friction materials. You see that the chairs have no wheels because of that. Otherwise, in strong seas states, you would just move around. And same for your equipment on the desks. The communication equipment was here in the rack over here, and what it commanded was this thing. This thing is 3 hydrophones. One is a tweeter, one is a mid hydrophone, one is a subwoofer, basically, if you were talking about audio systems on land. But the meaning is the same. So low frequency, mid frequency, high frequency transducers, plus electronics, and a structure that makes it more stable when you lower it from a crane. So you enter this kind of experiment, and the experiment already has a lot of organization around. For example, part of the organization was was done by NATO and was related to deploying equipment. Receivers, first of all, are a vertical array of 4 hydrophones. Oceanographic equipment, like a Doppler current profiler that finds current patterns. Transmitters at different locations. And a bathymetry scan to check the sea bottom shape and see where to deploy. These are 3-dimensional and the top version of the bathymetry. And of course, lots of practical issues. So, for example, you would deploy your equipment. You would use cables because communication is wireless, but you want to do the logging using reliable means, including cables. Cables cannot just be deployed on rocks, otherwise they would basically strain and get broken over a long time. So you understand all these things. You need to tie them to a chain and so on. And here, our lab, not sure where you would place your own working point. Ours was over there. And indoors, the situation is you basically deploy your equipment in the best way you can. First of all, on the roof, you would put, a differential GPS transmitter and an antenna to talk to the ship when it is available. And here, you would also put, for example, a connection to the satellite network of the NATO Research Center that would give you internet access. And in the indoor lab, you would have typical lab equipment for post-processing the signals. But one of the nice things is this one. So one of the hydrophones was connected to a real-time streamer that would enable you to see the signals being transmitted. So if you remember the previous Janus version 1 signal, here you see it. And of course, you need all ancillary equipment to keep you fresh. That was near end of August, beginning of September. It was very, very hot. So the experiment was done, one of the experiments, of course, was done like this. The ship would come from the Elba Island, and then we'll start doing some trajectories like this L-shaped one, and move north, southbound, east, westbound. And you would have transmissions over these legs in different bandwidths of that Janus signal that we had before. So, for example, you could already use the signal as is to estimate the ship velocity. Raw estimates of the ship velocity is unfiltered would be here in green and red. Green and red differentiate between the receiving hydrophones, doesn't matter. But you could use it for this. You could also use it to do some other experiments. So one of the other experiments that we wanted to do related to power control. And the power control here would simulate a case where basically you have several connections that should coexist. This node B would not transmit to node A too loud so that it avoids making interference to node C. So if you decrease the power, both can coexist, of course. Nice enough. We're talking about 2009. Power control required a lot of manual steps at the time. Now, most of these steps can be reasonably automated with more modern hardware. But in general, you would have to stop acquisition from the hydrophones, download hydrophone data, run a detector, estimate the SNR, and then understand whether you should change your power and start acquisition again after changing the power. Now, the power would be changed manually by calling the ships and telling them, look, you need to decrease 10 dB or whatever. So in this experiment where we have the 2 receivers, H2 and H4, we would, for example, decrease power a couple of times, and this would reduce the signal excess here and equalize the received power. So in this case, the power control worked using that very manual but effective anyway set of commands. So I don't want, I just want to give you a glimpse of the main difficulties that you may encounter. So I don't want to delve into this. But anyway, you get a lot of data during a few weeks of experimental activities. You understand how ship deployment is challenging. You have to avoid erosion of equipment. You know that once it is deployed, it is deployed. You don't have time to think, usually, especially you don't have time to program. So you need to come prepared with all your software in place. And when you recover at the end of the experiment, you can expect all sorts of things to attach to your equipment. So you can expect biofouling. It's known by everyone who deploys equipment at sea, but you see fish eggs and all kinds of algae, and even broken equipment over here. This is particularly special because this was a hard plastic, so-called Delrin case that anyway was pierced by something. So in any event, besides the biofouling, of course, we always say that we do the research in this field because you do your experiments at sea, and that's definitely one of the perks of this kind of research. But anyways, the important points are that you plan ahead, you bring as much spares as you can, of course, you repeat your experiments multiple times, which is boring, but definitely needed because you never know what is going to go wrong and you have multiple attempts. You keep adapting, and by adapting, I mean trying to understand which equipment to use or where to move it if you can, and to reorganize over the place and in real time as you need it. So other important thing, you download your data immediately and you write a few notes about it, peaks included, because then you will forget. And if you have many things to do, the experiment is the only time when you can reasonably do a first initial processing and data sharing. So they seem trivial things, but for someone that came from experiments done in the lab using computers, doing this was a discovery to me. So anyway, this presentation is called A Tale of Friends and Foes. And why is the tale of friends and foes? Because it seems, by any practical means, that underwater channels hamper any kind of typical propagation, typical communication issues that you normally have due to propagation effects, due to having lots of reverberation, due to having very low propagation speeds, so long propagation delays. But by all practical means, these things can help if leveraged properly. So one of the first things we will check is how underwater multipath propagation meets localization. So what is the key idea? Let's take a scenario. This scenario is San Diego, the San Diego Bay Area. And let's assume that we have one receiver over here, the red diamond, and the blue circle and the yellow-orange triangle here are two transmitters. So let's run the ray tracer that we had before, and let's check what the echoes and the so-called channel impulse response would be at the receiver. So this would turn out to become like this. If you transmit from the blue, you get this map of arrivals. So basically, the signal would come with a few spurious echoes here, would come with a few strong echoes here, some of them very close in time. And then there would be multiple other echoes that come at later times. All these are reflections of your signal of those surfaces that can interact with the signal. So we're talking about the sea surface, of course, and we're talking, of course, about the sea bottom. So there may be multiple reflections of these boundaries of the environments, but in general, the significant ones would display like this. So over a slightly different time scale, note that the time scale here is different, you would get a much different footprint if you transmitted from a sufficiently different environment. So you see that here the maximum depth is deeper, and that there is more variety in the bathymetry profile up to the transmitter, to the receiver. So because the channel impulse response, so the collection of these echoes, is so different, maybe we could leverage this difference in order to localize the node, in order to understand where the node was transmitting. So if we see something similar to this, we would localize the node to be close to here. If we see something similar to this, we would localize the node close to here. So this is very similar to wireless terrestrial radio fingerprinting, but not quite, because if you would just fingerprint, it just wouldn't work. Underwater channels change, and you would never be able to follow up with enough measurements. So the idea here is that we want to localize using a single receiver, which stays in the middle of these radar plots. And then we want to localize something that moves. It moves along this trajectory. And ideally, we would run a few simulations, run a few Bell runs for each of the points on this polar grid. And then we would try to understand from the transmission to which of these simulations it is more similar. So what would we do? We would, for example, see that there is similarity with these points over here. Some of them will be close to the actual location. Some of them will be spurious reflections that simply correlate well. Here you see that the guy moves along the line and then some reflections tend to occur. Here it keeps moving. The strongest reflection is here and the strongest correlation with the grid position is here and not close to the device. It can happen. There may be spurious reflection all over the place, and then we want to run some processing algorithm that estimates a most likely trajectory through the points that we have found. So in the end, the main issues that you may find, sorry for the bad formatting, are that you have multiple matches and that simply fingerprinting is not feasible. You cannot just go in the sea and measure at all these locations. It's time consuming, nobody would do it. So we simulate, we basically derive our database of channel impulse responses from ray tracing. And then we use a trellis search procedure to eliminate spurious estimates and fuse the location estimates. So what do we do basically? So typically, you would get channel impulse response. And this channel impulse response gives you, if you simulate it, several components. So these components would have a history of reflections. Maybe some of them are surface reflected. Maybe some of them are surface and bottom or just bottom reflected and so on. So surface reflections are usually quite specular. Unless the sea is in a very strong state with very high waves, the surface is more or less a mirror. So our idea here was to use specular, the direct arrival, the so-called specular arrival, and surface reflected arrivals to do a first correlation and estimate the range and depth. And then we would do a proper sort of fingerprinting and include all arrivals. So first, we try to match against the distance and depth. And this is very important because if you try to match against distance and depth, everything else becomes easier later on. And only as a second step, you find the bearing. So you have to find 3 dimensions, of course. One is the depth, one is the distance, one is the azimuthal angle of your location, so the so-called bearing. And we keep a given number of points that achieve the highest correlation values. And when you do distance depth estimation, you can get maybe good correlations and some spurious estimates. But for example, if you do it well, if you correlate with the right distance, you are basically here. If you correlate with wrong distances, you typically get lower correlations. And ideally, if you do a wrong estimation of depth and distance, estimating the bearing is much worse, much more difficult than estimating it with the right depth and distance. So in the end, your search for the point that best correlates with the location of the transmitter is easier if you solve this depth and distance estimation steps first. So let's say that you have found several likely estimated locations. You sort them by likelihood, and then you set a trellis where 2 points at different measurement epochs are connected if the two locations could have actually been walked by the device in the time that separates the two measurement networks. So if these 2 points are too distant, for example, P2 and P3, they would just not be connected because maybe there is no way that the device could have moved from here to here in a reasonable time. And then in the end, you do it for a number of measurements, NL, and you get your trellis completed. Now you do forward-backward path estimation that tries to obtain the most likely trajectory between the points of all likelihoods that are connected in the trellis. There are a few more details here, but in general, this is the main idea. And when all goes well, this is a simulation, what happens is that you are here, and your steps make it possible for you to get a few possible points that connect well to the channel impulse response that you have received. Maybe some are close, maybe some are far from your receiver. And by doing some initial cleaning and distance and depth estimation, you avoid to estimate some wrong bearings like here. So all your estimates go go closer to your distance, to your actual point. And then if you start fusing multiple points while the element here is moving, you can get a trajectory with a good accuracy, reasonable accuracy by all practical means for maritime applications. And some results. So one of the nice things is that this scheme is not very sensitive to SNR. So of course, very high SNR gives you the best situation, like the probability that the error in your distance estimate is greater than this abscissa in meters is quite high, whereas quite low. The probability is quite low, and basically you get errors that are very reasonable. If you go into the angular estimation, it gets also very good. You always have a tail of errors that hopefully get filtered out using our trellis search. Now, what the scheme is sensitive to is bathymetry. If you do not have a good bathymetry estimate, your error goes astray very fast. But the good news is most of the systems to estimate bathymetries, so the so-called eco-sounders, they tend to have a very, very high accuracy. So the error they make may be on a few centimeters. So we're much closer to the purple line than we are to the dashed blue line. So all of this is good, and it encouraged us to do an experiment. So we went to northern Israel and used 2 ships, one ship and the rubber board, actually. We mapped the bathymetry, and we got a profile like this. So we went into an area where there was a lot of diversity in the bathymetry, at least a very high slope like this one. And we have a receiver over here that was our, let's say, buoy, the one that would receive the signals and try to estimate the transmitter. And we had a moving transmitter track. Everything was drifting, so we actually had to correct for this drift later on. I'll save the details. But anyway, the principle is the same. So here you see a spectrogram of what we were transmitting. So this is the echo sounder of the ship that keeps the ship from grounding. And this is the chirp, the linear chirp that we transmitted to estimate the channel impulse response of the channel. So all the reflections that we would receive. And later on, receive and compare this with a database of ray tracing channels, ray traced channels. So our C-trial results go into this, for example. This is a run of 9 transmissions. In these 9 transmissions, our true location is in green and was updated over time. What we see is that our algorithm, which is the red triangle, tends to get estimates quite close, sometimes closer, sometimes not as close to the true location. And other algorithms, including a naive benchmark and aided version of the Viterbi algorithm, would actually not be as good. In particular, the best benchmark finds the point of highest correlation, and sometimes it just goes astray. So you need filtering. That's the point. We did filtering because it is needed. And if you get all the results together, our algorithm would estimate the node to be at these 4 points over time, over those known 9 transmissions. The point would actually be here, but still the error here is in between a few tens of meters, and that's very good. The other benchmarks would have a higher error in the best case of the blue triangle, but much higher and a very different azimuthal angle in different conditions. So in general, what we see is that we do this kind of sort of ray tracing aided, if you will, pseudo fingerprinting. We would do a search based on the correlation of the specular and the surface reflected arrivals. We would then do a trellis search to find the location of the device over a few measurement points. And then we would obtain a total localization error between, let's say, 200 meters and 300 meters, which is okay and acceptable for several practical applications of underwater localization. Considering that we have a single receiver, this is quite a good achievement. And so this was a first example of what kind of exploitation you may have for underwater channel impulse responses. Now, I hope I convinced that it is useful to try to decompose the structure of a channel and relate it to some physical characteristics of a transmitter. In this example, sorry, this is done to localize the transmitter. Now, for the second part of this talk, I want to go into security. And the first thing I will talk about is how to make underwater acoustic propagation delay and other features meet privacy. So basically, in this work, what we tried to do was to consider that we finally actually have a network of devices that communicate possibly over multi-hop routes. So not all devices are actually connected. And sometimes if a transmitter, legitimate transmitter called Alice, would have to talk to a legitimate receiver called Bob, it would probably have to use a route that goes through other nodes like these ones that would function as repeaters, as relays. And then there would be someone here that would try to attack this communication by eavesdropping on it. So what do we want to do here? We want to give Alice and Bob a means to obtain secret information without explicitly transmitting messages, explicitly transmitting secrets that may depend on some local secrets. So by all practical means, we don't want them to necessarily make a Diffie-Hellman exchange, for example. So we want to harvest randomness from this network, and we want this randomness to be partly, at least partly, secret to the eavesdropper. So what do we use as the source of randomness? We use the propagation delays along the routes. Note that this is a network which will be assumed to be a realistic network. So in all our realistic simulations and our experiments, these will be drifting nodes. So the propagation delays are not constant, which is very important. Otherwise, Eve would have a very easy time eavesdropping and breaking the secrecy of this. But it is actually a varying and random source of, so it's a varying source of randomness, and in particular, because the delays change with the random drift. So how do you normally obtain a secret key in this framework called typically physical layer security? You typically measure the randomness source. In our case, you measure the propagation delay along multiple routes, and then you distill or convert these values into secret key bits. So for example, you measure the route delays over a number of routes NC, and you quantize them with a known resolution rho. This turns your soft values into a sequence of bits. And this sequence of bits can be your key. Then you would have, in a full framework, you would have to reconcile discrepancies that are inevitable sometimes in the keys perceived by Alice and Bob. And you would also have to finally single out bits that are actually secret to Eve, because Eve may hear part of the communications, and due to correlations, she may be able to eavesdrop on part of the key. So this is a step called privacy identification. And maybe you repeat the process several times and you obtain several secret bits. So what we will concentrate from now on is the distillation part. So the reconciliation and privacy amplification can be done using means and algorithms that are typical of all wireless communication systems, including terrestrial radio ones. Whereas the distillation part is more typical of, well, not more typical, more to be tuned towards underwater scenarios. So let's concentrate on that. So first of all, we have to measure the delays. To measure the delays, we have to propagate packets and measure these delays. Measure how much time it takes to get the packets to the sink, for example, from a source to a destination, from Alice to Bob. So we send an RPing, and we reply with an RRAP. The RPing propagates through the whole network. The nodes repeat it. And when they repeat it, they keep recording their own ID inside the packet. Very easy. So you keep track of who repeated the packet. When you are done, you are basically measuring all the routes from the source to the destination and all the routes from the destination to the source. And basically, if all goes well, the routes are the same. There have not been too many errors. And you measure propagation delays over a network that has not changed too much. So you measure the same thing, and someone else would not be able to do the same. So one practical issue is that these messages that go back and forth need to store the route they travel, and that any practical transceiver would introduce a delay in this kind of processing, where it takes time to transmit the packet, and the delay may be random. So this is a source of randomness that you may want to harness, but it is also something that increases the discrepancy between Alice and Bob. So we decided not to harness it, but rather to set the retransmission time of every node controllable. This makes it easier to control the situation. And if you have multiple routes, you need to decide which ones you use to sample the propagation delay and make a key. Now, we used one algorithm. It is not important which one you use. The important thing is that you use the same algorithm at the source and destination, or the key will not match definitely. So the general scheme is then the following. You broadcast this RPing message. You do the propagation by keeping your track of all the relays, and Bob, so the legitimate receiver, would choose the routes, extract the key from the delay of these routes, and then broadcast back a route reply, so that the route reply gets forwarded through the network, and then Alice would be able to compute propagation delays through all routes, and choose the routes from which the delay is extracted, quantized, and a key is made. When all goes well, the keys are the same. And what is Eve doing in the middle? Eve is trying to collect these messages, note down the connections between the nodes. So who is connected to who is talking to whom, and in this way, try to make up the topology of the network. If you can make up the topology of the network, you can reconstruct the key, of course. And in order to do this, however, you have to reproduce the topology of the network. And in order to do this, Eve can try to leverage the message it overhears by applying then some algorithm called multidimensional scaling that basically reconstructs, sometimes is able to reconstruct the network topology by using a proxy for the delay, for example, by trying to use distance as a proxy for the delay. So in this case, sometimes Eve can be lucky enough to hear enough exchanges, and then it would be able to reconstruct possibly the topology. Sometimes it will not be able, and in that case, it would possibly fail to attack. Of course, if Eve sits on top of Alice and Bob, then it's easy to reconstruct the topology because you are in the middle of things. But at the same time, it is very unlikely for Eve to be able to get to the position of Alice and Bob because this is a random network, you don't know the locations, you drop your eavesdropper, but you don't know the location. So in general, let's assume that here is a partial knowledge of the network. So what is the main trade-off here? So if the network were fully static, so no movement at all, no matter how much Alice and Bob would repeat the delay measurements, they would always get the same secret bits because the delays are always the same. They are your source of randomness, no randomness here. If the network devices instead, at the opposite case, move very fast, then Alice and Bob would always measure different route delays and never be able to agree on a key. So the method here needs some middle ground. You need a dynamic network, but not too dynamic, so that you have a chance for Alice and Bob to be able to agree on this secret key. So you do simulations. You see that at least in simulations with static network realizations, Alice and Bob are able to find very well matching channel realizations. If you check the relationship between the channel realizations, the delay realizations of Alice and Eve, you see that there is much less correlation. So this is 40. It means that the method has some chance to actually work. So you start doing some more accurate simulations where you have nodes drifting and you have faithful acoustic propagation through Bellop, and you have to estimate these delays from Bellop. And for example, one of the things we saw is that if you measure the effectiveness of the method by how the keys derived by Alice and Bob are similar, you compute the Hamming distance basically, so the number of different bits, you see that as the routes increase, the method can still work very, very well. You have an average Hamming distance of less than 1. So sometimes you may have one error, up to one error, or a few more. Sometimes you have 0 errors, which is what we want. But the key inferred by Eve is typically has a much higher error, except that if the network is very rich and there are many routes among the nodes, then your Hamming distance, so the error that Eve makes, is much lower. And this is the drawback of the method. If the network is very rich, then Eve has more chances to see messages going around and to understand the topology of the network. This is the reason why it fails less in a way. So we went to the Caldonazzo Lake, close to the Levico Lake, for those of you who know the area of Trentino to Adige. And basically, we went to the nautical center of the university and made a trip with a few boats and basically measured the propagation delays in different topologies. So here, between these two, only the position of Alice and Eve changes. And here we put all the nodes all together to have a rich network topology. So what we saw is that in different, one thing is in different resolutions of the quantization of the delays, we get that Alice and Bob tend to find a closer key than Eve. However, of course, if you want to increase the resolution, increasing the resolution masks the errors in the propagation delays, for example, but also gives Eve a good advantage because, of course, it reduces the error that Eve would make. So maybe you want to get to resolution 0.1 in order to keep the Hamming distance of Eve high enough, but keep the Hamming distance of Alice and Bob low. So the method works in a way, and it works both in realistic simulations and in actual sea environments, well, lake environments in this sense. Now, I don't have much time left, so what I would like to do is finish up with another different mode of extracting randomness and form a secret key, which is also part of the contributions that we published with colleagues from the University of Padova in the context of the Sextet project of Restart. And basically, what we did before was to use a macroscopic propagation delay over a whole multi-hop route in order to obtain randomness. Now, let's obtain randomness from the channel impulse responses, the same channel impulse responses that were used to to localize in our first work of today. So let's say that you go at sea and you measure a channel response like this. Over time, in milliseconds, you see some significant arrivals and some low power reflections. This is a real measurement, by the way. And you want to extract a few features from this. So one is, for example, the number of channel taps. Taps is a jargon for significant arrivals. For example, 1, 2, maybe 3, 4, 5, 6 significant arrivals over here. You want to find the root mean square delay of these significant arrivals. You would want to find the root mean square amplitude of each significant arrival, and you would find the channel delay spread as a macroscopic measure characterizing the whole channel impulse response. So let's say you take these 4 features, and you want to use them in order to create a secret key. The procedure is the same. You need to distill something, so you need to measure these features, and then you need to quantize them. From the quantization, you will extract a sequence of bits which makes up your key. Now, how do you measure the features? So in order to avoid, let's say, the word is systematic errors in the measurements, what you want to do is possibly to send a signal. This is a real spectrogram from an actual transmission. So you want to transmit a signal. The signal is a ping, maybe. The ping is received by Bob. The reception is this smeared part in greenish over here. Then Bob would answer, and the reception is here at Alice. This serves as a way to measure the propagation delay. Alice does some calculation, and then it sends a synchronization probe. And it is a synchronization probe because Bob knows that in this way, the two-way propagation delay is also known to Bob. So you have all in place to do a calculation and understand how much it takes for the signal to propagate from Alice to Bob. If it takes enough time, you have a little bit of time to transmit these chirps, which are then used to extract the features, and do it simultaneously. So by computing how much time it takes for you to transmit, you receive this probe packet, and then you know that after some propagation time, you need to transmit your own chirps. And if you stop early enough from a computation that is easy to be done from these numbers, you will receive the signal from the other part. So basically, you are measuring the channel simultaneously. So this is the best kind of doing a measurement, because if a channel is sufficiently reciprocal, in this way, you will get it. So what is the key idea? The key idea is to have a method to measure channel in a way that makes the measurements as reciprocal as possible. Now, you could take the measurements and extract a key directly from the features. This was done previously in 2021 by Pelekanakis et al., for example. Or you would extract the key from something more stable. For example, the parameters of the statistical distribution of the features. Basically, you could fit a Gaussian distribution to the features and get the parameters of the Gaussian distributions. You have 4 features. The Gaussian distribution has 2 parameters, so in total 8 parameters. And basically, the features are these means and variances, so the parameters of the distribution. You sum them for all features and parameters, and you get this soft key eta. So comfortably enough, the difference between the values of the soft key for Alice and Bob are centered at 0. And the more centered at 0, the lower you move, the slower you move, let's say. So remember that this eta is the value that gets quantized to get a soft key, to get the hard key, to get the actual secret key. So it has to have a little difference. Now, the other ingredient of this is to quantize the values of the soft key in a way that leads to as few errors as possible, and in an optimal way to extract secret bits. So to do this, we take the values of the soft key from Alice, we take the values of the soft key from Bob from simulations, and we decide that by clustering these parameters, the soft key should be quantized by taking the value of these centroids and working under a minimum distance criterion. So this improves the quantization, and good enough if you measure, for example, in conditions of normal SNR, signal to noise ratio, you measure what is the difference between the keys of Alice and Bob and the keys of Eve and Alice, so if the eavesdropping was successful or not, well, Alice and Bob have a quite good coincidence of the keys they measure, whereas Eve and Alice have many more errors. So this is quite important because it gives you a higher likelihood that your keys will not be eavesdropped by Eve. In particular, quantizing with our method made it possible to extract about at least 3 times as many secret bits than with a naive uniform quantizing. So we did an experiment about this, and then I'm going to conclude. We did an experiment about this. The experiment was in the Kumbor Bay in Montenegro during the Breaking the Surface conference a couple of years ago. And basically, we then used those experiments as experimental data to prove our concept. And you see that in our measurements, sometimes the coincidence of the measurements is very, very good. Like in this case, these are Alice and Bob in blue and red. And sometimes, for example, in some scenarios, you may have discrepancies. So maybe amplitudes are not the same. Delays maybe are the same, more or less the same. But by any practical means, in the end, the average Hamming distance between Alice and Bob is quite good. And the Hamming distance between Eve and Alice, so the capability of eavesdropping, is much worse. And so, in general, the channels, underwater channels, offer a good feature basis also for key generation. We're talking about network delay and channel impulse response features. I showed 2 methods to use this. Of course, you have higher chances that your method ends up in matching secret keys if you take reciprocal measurements and you compute and quantize the soft key values properly. But in general, the system is a working system. And like all physical layer security systems, it exploits the characteristics of the channel to achieve security. And so it does not require other hardware, maybe an external cipher, with respect to what you already have on a modem. So it is something that actually helps and would be useful to incorporate in general modem hardware. So I now do not have time, of course, to explain how underwater multipath propagation may help you meet authentication. So I'll just conclude here. And I'll take the general conclusions that, yeah, underwater communications and networking is often described as harsh and difficult. Harsh because of bad channels. Bad channels means lots of multipath, lots of Doppler spread and delay spread, difficult to coordinate. Yet these characteristics can turn to the advantage of algorithms that exploit such characteristics, such features of underwater channels. So we're talked about privacy and localization. We have a line of work on authentication that also successfully exploits multipath, but then we'll wait for the next party to make a new friend. So with that, I would like to conclude, and thanks to you, to all of you, for your attention. I really appreciate that you stayed until the end.